Section 10.4 is the cross product. This is another combination of vectors, a specific product for two vectors. You'll recall that with a dot product, we took a vector u dotted with a vector v, and we ended up with a scalar. A little bit different from that is the cross product, which marked by u cross v for two vectors u and v in R3. So each of these vectors has three components. U cross v results in another vector. The formula for which is given here. We can do this component-wise operation and calculate the value of it, or we can think of it as the determinant of a matrix which looks something like this. So we list u1, u2, u3, we list the vector v, and we list the standard basis vectors I, j, k, and we take the determinant of this 3 by 3 matrix. Now, one of the fastest and easiest ways to take this determinant is to just add or append the first column and the second column, and cut right diagonals top to bottom for the 3 complete diagonals, and then 3 complete diagonals back the other way. And this determinant looks like the following. We have u1 v2 times k plus u2 v3 times I hat. That's looking at each of these determinants. And the third one is u3 v1 j hat. v1 j hat. And then minus for all the red diagonals, so put that in a group. One big minus sign in front of everything. And that is u3 v2 I hat plus u1 v3 j hat plus u2 v1 k hat. And then we combine like terms. In other words, the I terms, I hat terms combine, the j hat terms combine, and the k hat terms combine. Since those are linear combinations of the standard basis vectors, we'll end up with a new vector. Down here is another formula, another version of the formula that we just saw before, expanding along cofactor matrices elements. So, 3 different ways to do this. We can use the formula given here, which is hard to remember probably. This is cofactor expansion of this determinant right here. Or we can use the 3 by 3 determinant trick, which is these 3 diagonals multiplied and added up, these 3 diagonals multiplied and added up, and with a minus sign in front. I think that anyone will do, whichever you prefer should suffice. So let's see an example. So here we're given a vector u equals 3, negative 3, 7, v is 1, 5, 2. Okay, so u cross v is as follows, and they don't tell us which cross product to calculate, so we just assume they want u cross v. We'll see later that u cross v is not equal to v cross u necessarily. And, well, we use the diagonal method again. So we set up u, then v, then I, j, k. Then we've added the first column and the second column, appended that. We're able to construct our diagonals, 3 times 5 times k, negative 3 times 2 times I, 7 times 1 times j. That's the whole line right here. Similarly for the red, we've got all the diagonals that cut back right to left with the standard basis vectors. And we're off and rolling. We combine like terms, 15k minus 3k minus negative 3k. We end up with 18k, and so on. We'll find the same value for j hat and the value for negative 41 I hat. And our vector then could be written back in vector form as follows. Okay, so that is a simple, straightforward cross product calculation. 2 vectors u and v. All right, now let's see what happens if we cross a vector with itself. We could always try this with a specific vector, but it wouldn't prove it for all vectors, right? If I tried to show that 1, 1, 1 cross 1, 1, 1 was equal to the 0 vector, well, it wouldn't prove it for all vectors. It would show it for just the vector 1, 1, 1. But if we carry that out, we'll see that that's actually true. But the question says, show that for any vector A cross A cross with itself is equal to the 0 vector. Okay, well, let A be equal to A1, A2, A3, just like we would with U or V or whatever, some generic components which are real numbers. That's the only thing we could say about them. And then we write down A cross A in its expanded form. That sets up this matrix right here, A, the vector A, and I, J, and K. Then we append the first and second columns, take our determinant, and start to combine like terms. What we see is that there's an A1, A2, K, that's positive, K hat. There's an A2, A1, K hat, that's actually negative. And this is going to happen for all the other terms as well. They add to 0. So each coefficient adds to 0, and we end up with the 0 vector. Okay, so 0 vector has no magnitude or direction, or it has magnitude 0 and no direction. So that proves it for any vector A now. Right? So any vector we could possibly come up with that's comprised of three real numbers is going to satisfy that identity. We know that without a doubt thanks to the proof that we just constructed here. So that's a theorem we can use in the future. Okay, so next up we've got a combined vector product expression. So notice that we have a cross product here and a dot product. Now there's parentheses to sort of guide us in this, so we should follow those parentheses. If we didn't follow those parentheses and tried to do this by finding this dot product first and then crossing it with this vector, we'd realize we have an incompatible argument, right? This dot product would give us a scalar, and then we'd be trying to cross this vector with a scalar, which doesn't make any sense. It's undefined, not a possible operation. So we want to make sure that the cross product is computed first. So we carry that out using the same method as before, and we end up with -7, 4, 10. All right, so that means our expression, E we've called it, down here is equal to -7, 4, 10, dotted with 2, 6, -1. Carry out the dot product, and it looks like we end up with 0. Okay, that's coincidental, but sure. That should be a scalar because it was a dot product. Next up, show that for any two vectors A and B, A cross B, and then dotted with A is 0. Well, was the first example coincidental? Let's find out. Can we prove this for two generic vectors A and B? Well, we let A be A1, A2, A3, B have components B1, B2, B3, just as before. And, well, we calculate this by doing the cross product first. And we'll dot it with A1, A2, A3 by the time we're done. This is the result of the cross product, all written down in its entry form. These are the I hat components, J hat components, and so on. And then we dot that with A1, A2, A3. We end up getting these 6 terms we see below. You see that A1, A2, B3, there's a negative A2, A1, B3 here. That adds to 0. These two add to 0, and these two add to 0. So in the end, yeah, the result of this is 0. Now, this was for any two vectors A and B. There is no constraint on them other than the fact that they both consisted of 3 real numbers in these entries. So it means that this is always true for two generic vectors A and B in R3. So it's a nice identity to have around. And it turns out there are a whole lot of properties to come that we'll see for the cross product. Now, one nice property is this theorem here. The magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of theta where theta is actually the angle between A and B. And that's the acute angle between A and B. So it'll always be between 0 and pi. Or, okay, the least angle, not an angle between 0 and pi formed by A and B, which all vectors have such an angle, every pair of vectors. So we're asked to verify this theorem for the given vectors right here. So we're not exactly proving the theorem, we're just checking that this theorem holds true for these two vectors. So A cross B, set it up with our determinant matrix, or matrix determinant. And what we get from that is negative 1, 0, 0. And then we take the magnitude of that, and we realize that that is 1. The magnitude of this vector is 1 using the magnitude formula. Okay, hold on to that. We'll come over, we need to check the left-hand side. So this was the right-hand side. We need to check the left-hand side down here. So the magnitude of A times the magnitude of B, well, we can find those magnitudes easily. So we have 2 and 1 for A and B's magnitude respectively. Now we need to find the angle between these two vectors. That's probably one of the trickiest parts. But luckily, the first component of each vector matches. So it means that we can just consider these two vectors as planar vectors. In other words, they're living at the same level on the x-axis. So they really live in the YZ plane. So we have a YZ plane right here, in which I've plotted root 3 comma 1 and 1 comma 0. So here we are in the YZ plane, the x coordinates matched, so we don't have to consider any x values in this because these two vectors are coplanar. In other words, they're in the same plane. With this information, we draw A, we draw B, and we draw the angle A and the angle B, and we're able to find the angle between them because, well, it looks like B is actually just this y-axis, this horizontal axis. So a little bit of trigonometry here. Looking at this right triangle that we have in the picture, tells us that the sine of theta right here is equal to 1, which is the opposite. This is a height of 1 right here, over the hypotenuse. Well, the hypotenuse is unknown, but it's the square root of root 3 squared plus 1 squared. And, well, it's 3 plus 1 is 4. We get 1 over root 4, and that's 1/2. So the sine of theta is 1/2. When we put all this together, we get 1 again. Okay, so it's just right triangle trigonometry once we realize that the x coordinate is the same, or the x component is the same in these vectors, and we can ignore it and treat these vectors as two-dimensional vectors. It's a nice trick. It makes this problem much more doable than otherwise. So we're asked to prove the theorem above. That takes quite a bit of time. The textbook has a very good demonstration of it. It's only about 6 lines long. It's easy to see how it comes about, but it's a matter of calculating A cross B's magnitude squared, which ends up being a dot product, and connecting that dot product to the right-hand side to show that those two things are equal. So the textbook's got a very nice example of that. Okay, so two non-zero vectors A and B are parallel if and only if A cross B is equal to 0. So that's a nice fact to have around. We know that two vectors are perpendicular if A cross B, or A dot B, equals 0. So this implies that A is perpendicular to B. Now we have a check using the cross product to show that two vectors are parallel. That's quite nice. Here we have a whole list of properties for the cross product. Be careful with these. Make sure to use them exactly. There's a lot of chances to prove some of these, and I think even some worksheet problems or homework problems might have you do something like that. So nice properties to keep an eye on.